In this video, we shall take a look at a difference between the discrete situation that we had discussed in SEM 1 with the density situation that we are studying now. Suppose that x and y are jointly distributed random variables. If x and y are both discrete, then so must be the joint distribution of x, y. We had already seen it in SEM 1, and the reason is that if x is discrete, then it can take only countably many values, and similarly for y. And as a result, the pair xy can take only the values xi, yj, where ij are both in natural numbers. Certain pairs may not be possible, but it can never take any value outside of this countable set. So, the set of all possible values that the pair can take is again countable. As a result, it is also jointly discrete. Since being discrete is the same as having PMFs, so I can say that if x and y both have their own PMFs, then the x, y pair has joint PMF. However, if I replace the word PMF with PDF or density, then this statement is not true. We are now going to discuss a counterexample. That is an example where x and y will be jointly distributed. Each of them will have PDFs, but as a pair, they will not have any joint PDF. The counterexample will start by specifying x. Suppose x has density this fx. Between 0 to 1, it takes the value 1, otherwise it is 0. Now when I say that here is a random variable, I of course means there is a capital omega on which it is defined. Now I need to define a y on the same capital omega, and I will do that very easily by taking y equal to x. So clearly they are jointly distributed because both of them are defined on the same space. They are actually the same. And y also has density, same density because x and y are the same. Shall now show that xy as a pair has no joint density. And for that we shall first try to find out the joint CTF of x, y, which we know always exists. Now here x and y are the same. So this probability is actually x less than or equal to minimum of x and y, because x is less than or equal to x and again x is less than or equal to y. So x is less than or equal to both x and y, which means it is less than or equal to minimum of xy. In order to compute this, I have made a little sketch of the density function. You can see that my x takes values only between 0 to 1 because only there the density is positive, otherwise it is 0. So if this minimum xy is less than 0, then I am certain that this is going to be 0. Similarly, if this minimum is somewhere here greater than or equal to 1, then certainly the entire area is to its left. So then this probability will be 1. Now if the minimum lands somewhere here, in that case I have to find out the area to the left of this, and that will be this area. This is minimum xy and this is 1. So the area will be base times height, that is, it will be minimum xy if this holds. Our aim is to show that this CDF does not admit a joint density. Now how do you show that? Well, we shall try to differentiate this and we will get that mixed partial del square f by del x del y. We know that if joint density exists, this has to be the joint density. So we shall show that this will not be a density function. And immediately we can guarantee that no density can exist. To simplify our computation, what we will do is we shall denote this thing in a more pictorial way. This is our R2. I am going to show the value of fxy in each of these places. It should be quite easy to see. If my xy is here, then the value of fxy should be 0, because then both x and y are less than 0, so their minimum must also be less than 0. In fact, it will be 0 even here, because here x is less than 0, so the minimum is less than 0. Similarly, this will also be 0 here. Similarly, this case means minimum is greater than equal to 1, which means both of them are greater than equal to 1, then it is 1. Now, for this part, the minimum is y, because y is less than x, and that minimum is less than 1, but it is positive, so we are in this situation, so here it will be y, and by symmetric argument, here it will be x. So these are the simplified version of fxy over different parts of the plane. Now our aim is to partially differentiate it twice, once with respect to x and then with respect to y. Observe that none of these things involve both x and y simultaneously. So when you differentiate both with respect to x and y one after another, everything will turn into 0. So this function will just turn out to be identically equal to 0. The function identically equal to 0 of course cannot be joint density, because the total volume under the surface must be equal to 1. So we see that this cannot be a joint density, and we know that if this is not a joint density, then no other function can be a joint density. Hence we have shown that xy, the pair, has no joint density. Here we are again working with x with the same density as I discussed earlier. But now instead of taking y equal to x, y equal to x squared. The question is, does x comma y have a joint density now?